Okay, so lecture 3.3 is called The Climate System, and it is a little more earth science in nature than sustainability, perhaps. What I'm trying to do in this lecture is for you to be able to, by the end of the lecture, be able to explain how our climate system works in sort of basic terms. I, of course, don't expect any of you to be experts in our climate system, and you don't need to be experts in our climate system. But in order to understand climate change and global warming, you at least need to have some very basic understanding of how our climate system works and how it works to maintain our energy balance, to maintain our temperatures and our climate system within the Earth. So that's the focus of the lecture today, is to go over those basics and how that contributes, how sort of the basic climate system contributes to climate change. So if it's a little bit more sciencey in nature today, that's why, and that's the motivation and how it all works in with climate change as a whole. So we have 5 key terms that I want you to focus on today in our lecture. And these will be key terms that you will see in the practice quiz and also in the final module quiz as well. So the key terms are insulation, albedo, positive feedback mechanism, negative feedback mechanism, and the weathering feedback. Okay, so what controls our Earth's climate? Now, I'm pretty confident that at one point in time, you guys have learned this information. Either in middle school or in high school at some point, you probably took some earth science courses. You may have also studied this information if you took Geography 221 or other similar courses at K-State. So hopefully this is refresher information for some of you, and this will trigger memories of things that you have learned in the past. Our climate system obviously begins with energy from the sun. Everything in terms of our temperatures, our weather, how much rain, precipitation, snow, cloud, all of that is a function of our energy and our energy balance. So what we have illustrated here is all of the interdependent aspects of Earth's climate system and how that's relative to the Earth's energy balance. And so what you're seeing here is we have the sun, the arrows that are coming down from the sun is the energy, the heat that's coming off of the sun, that's entering our atmosphere, and then it's showing how some of that is absorbed by the earth, some of it's reflected by the earth, some of it's reflected by clouds, some of it's reflected by gases in the atmosphere, some of it's absorbed by our ocean, some of it's absorbed by our trees. There's just a wide variety of interdependent aspects of Earth's climate system that are absorbing, reflecting the energy from our Earth. So it's complicated, obviously, and a change in one part of the system is going to change other parts of the system. So to help explain this probably a little bit better and a little bit more eloquently, I have a short video here, a few minutes long, of how our climate system works and some of those aspects of Earth's energy balance. So go ahead and pause the slide presentation and watch the video and then come back to the presentation. So as I've said, and as the video has already also said, there's really two things that drive Earth's climate system. The main driver of Earth's climate system is obviously the sun and energy from the sun. Energy flows into the earth from the sun and flows out of the earth and the atmosphere when it is radiated back into space. Eventually, all energy does radiate out into space. How long the sun's energy is trapped in the atmosphere is what determines our climate and our global temperatures. So energy from the sun is our main driver of Earth's climate system. How much of that energy is moving in and out of our atmosphere. The other main driver is the way in which heat moves around our atmosphere and our oceans. Those are the two main drivers. But really, Earth's energy balance is the amount of sunlight that shines on the Earth, which is this term of insolation, which I'm going to explain in another slide, and then all of the characteristics of the Earth's surface and our atmosphere that act to reflect, circulate, and re-radiate our energy. Those are the two things controlling Earth's energy balance. So let's talk about the first one first, and that's insolation, the amount of sunlight that shines on the Earth. Insolation is a measurement of how much solar radiation or energy, same thing, that falls on any given surface. It's the key factor that determines the climate of the Earth. It's the key factor that determines why the equator is warmer than the poles and why we have seasons. So sunlight falls most directly on the equator. You can see on this figure that I have on the slide here, near the poles, the sun's energy strikes the earth at an angle, which spreads that energy out over a larger area. So and then at the poles, the solar radiation hits the earth more directly at not an angle, and so the heat from that solar radiation is much more concentrated into a smaller area. So each square mile of land or water at the equator receives much more energy, much more heat from the sun than the poles, because at the poles it's spread out over a wider land mass. So this means that it is hotter at the equator because the same amount of energy covers twice as much of the area when it strikes at the poles than when it strikes at a surface directly, like at the equator. The energy striking the earth the energy from the sun that strikes the earth indirectly, so at the poles, has less ability to warm the earth because there is less energy per unit of surface area than when the sunlight strikes the surface of the earth more directly, like at the poles. So again, just to reiterate, this difference explains why the equator has a hot climate, why the poles have a cold climate. The differences in insolation also help explain the existence of seasons. For many years now, since we've had technology to do this, satellites have been able to monitor these energy flows. So they use these machines called spectrometers that measure how intense the energy is at different wavelengths flowing into the earth and then back out from the earth. So this here is a picture of those maps that are created through satellites and through spectrometers. Um, and it shows how much more concentrated heat is being absorbed at the poles than at the equator than at the poles. And you can, if you're interested, you can get online and Google insolation spectrometer maps, and you can see that this concentration changes by season, um, and um, sort of on a regular basis. The spectrometer mapping will look different depending on the month and the season. So that's insolation. Another important part of all of this is related to orbital variations. So this is also a refresher of information that I know you've learned before. Our Earth does not orbit around the sun in a perfectly circular orbit, right? It's much more of an oblique or an oval. So at some points in the Earth's rotation around the sun, we're closer to the sun, and at some points the Earth is farther from the sun. This means that the insolation also changes. So it's not just a matter of equator versus North Pole and South Pole. It also is the amount of insolation is also a factor of what stage of the orbit we're at and how far our orbit is from the sun versus how close it is. So as the Earth is closer to the sun in the orbit, the more concentrated the solar radiation is and the higher the insolation. Earth's orbit also is not fixed. So the shape in which we are orbiting around the sun is an oblique, but that oblique changes shape over time. These changes also change, obviously, the total insolation and the timing of the insolation. So these orbital variations have made a big difference in conditions on the Earth during the period of time in which humans have inhabited it. So these variations in orbital cycles are what have led to things such as ice ages or periods of increased tropical temperatures throughout the Earth, is because the orbit of the Earth has changed. Okay, so that is a summary of insolation, and it's a natural effect. It's something that, obviously the angle at which the sun's energy is hitting the Earth and the orbital shape of which we are orbiting around the sun are natural occurrences that humans do not have influence over. So these are natural causes of climate change and changes and variations in Earth's climate over time. Another important factor in all of this, in our Earth's climate, and also a natural factor in Earth's climate, is this concept called albedo. Albedo is a measurement of how reflective a surface is. The more reflective a surface is, the higher the albedo. So if you want to think about this in terms of a mirror versus a black piece of paper, the mirror is going to be more reflective. It's going to have a higher albedo. The black piece of paper is going to be less reflective, have a lower albedo. How this relates to the Earth's climate and the Earth's energy balance is that we have areas of the world that are dark and we have areas of the world that are lighter. The more reflective the surface is of a certain part of the Earth, the higher the albedo. So snow, ice is going to have a higher albedo. It's going to reflect more heat, and it's going to send a greater amount of the sun's energy back out into the atmosphere and space. The darker the Earth's surface, so ground without ice, dark water, dirt, sand, those sorts of things that don't have snow or ice absorb more of the heat, which means less of that sun's energy is leaving the atmosphere because it's being absorbed by the non-reflective surface. So the summary is dark surfaces absorb more of the sun's rays and heat the earth to a greater degree, while snow reflects more of the sunlight back into the space and cools the earth's surface. So this leads to something called the ice albedo feedback. And so I'm going to again have you pause the slide presentation and watch this video so that we can gain some greater understanding of the albedo effect and albedo feedback. All right, so hopefully it's starting to come together now. What's important in this is this idea that there are feedback loops that are happening and that are naturally occurring feedback loops. A feedback loop in general is anything that amplifies or diminishes something. So we have all sorts of feedback, not just related to climate change. Feedback in general is the process in which changing one quantity changes a second quantity, so cause and effect essentially. And then the change in the second quantity in turn changes the first quantity. Positive feedback amplifies the change in the first quantity, while negative feedback reduces the change. Climate change feedback is important to understand what is driving climate change, because climate change feedback processes either amplify or diminish the effect of climate forces. Again, feedback in climate change feedback is generally naturally occurring forces that are either causing climate change, climate temperatures to continue to increase, or climate change, global temperatures to decrease. So let's first look at this in terms of what a positive feedback mechanism is. Now, I want to make it really clear that the word positive, we generally, when we hear the word positive, we think it's something good. When we are told, when we're given positive affirmation, we're like, yay, we did something really well. Well, actually, in the world of climate change, positive feedback mechanisms are not always a good thing. So we have two pictures here, and this should both show you how positive feedback mechanisms work. So let's look at the figure on the left, and we'll start with the cooling. We'll start with cooling. Yeah, so we'll start with the cooling step. You really could start anywhere along here, but say we have some naturally occurring event that happens. Maybe it's just naturally wintertime, or we're at a stage in the Earth's orbit around the sun where we're farther away from the sun. Whatever, we have a cooling that happens globally. Cooling generally leads to an increase of ice growing on surfaces, water surfaces. When you have more ice growing, you've increased the albedo. We have more reflective surfaces. That means that more of the energy from the sun is being absorbed, less of the sun's energy is being absorbed, more of it's being reflected and sent back out into space. If there's less energy being absorbed, we have a cooling effect. Earth's temperatures decrease. So the more ice you have, the more reflection you have, the less energy that's being absorbed, the cooler that it gets. So that's a positive feedback loop. You can also have a positive feedback loop where Earth's temperatures actually end up increasing. And this is where we're at currently. We have over time seen a warming trend within our global temperatures. As it gets warmer on the Earth's surface, more and more of our ice melts. If we have less ice on globally, we have a decrease in our albedo. We have less reflective surfaces to reflect sun's energy back out into space, which means more of the sun's energy is being absorbed by the earth, by our land, by our oceans, which means temperatures are increasing, which means it's warmer, which means more ice is melting, which means our albedo is decreasing even more, which means it's warming up. And you can see how this is a positive feedback mechanism because one thing triggers a change in the other thing, which then triggers the first thing to change again. But in our current situation, this is negative because it means as more ice melts, as our albedo decreases, we absorb more sun energy, it gets warmer, which means we just continue that loop. So you can see on the left-hand side, we have a positive feedback mechanism that cools the earth. On the right-hand side, we have a positive feedback mechanism, which is actually warming our earth. Positive feedback mechanisms lead to what we refer to as runaway change. If such a loop continues for long enough, we could result in the entire earth being covered in ice or the entire earth having no ice and being in a situation of tropics. So, for example, the climate cools, which is the initial change. Snow, which has a higher albedo than bare ground, covers more of the surface. This increases the amount of sunlight that's reflected back into space, which cools the earth even further. Since this chain of events that I have right here furthers the initial change that triggered the whole thing to begin with, it's called positive feedback. And remember, just because it's called positive does not mean that it's necessarily good. Positive feedback mechanisms tend to lead to runaway change. Change that unless there's some type of a massive jolt to the system, we cannot get ourselves out of. Small initial change is accentuated into a major change. And then this runaway change that I've described here, where the earth suddenly cools and we're in an ice age, the exact opposite can be true where we warm up to a stage where we are too hot. Okay? So that's a positive feedback mechanism, which is the figure that we see here on the left-hand side. This process of weathering is a negative feedback because we are able to change the direction in which global temperatures are occurring. It has beneficial results generally, but it's called a negative feedback because it works in opposition to the change that initially triggered it. So that is weathering feedback, and that's a negative feedback. All right, so hopefully it's starting to come clear to you that we have two things that are driving Earth's climate system. The main driver is energy from the sun. How much of that energy is being absorbed, how much of it is being reflected back out into space. And then the second thing is the way in which heat is being moved around our atmosphere and our oceans. What we're going to do in the next lecture is look at how heat is absorbed and or reflected. So what are greenhouse gases and why is it that greenhouse gases are trapping heat in our atmosphere?